This video is a preface to a whole series of videos that I will have for Maximum Entropy, otherwise known as MaxEnt, in the context of statistical analysis. These videos are meant to accompany a much larger and thorough course on the topic that I've created, and you can find a link for that course below. The overall goal is to show how MaxEnt methods can be used for statistical analysis. And it's important to point out here that the methods that I'm talking about are an alternative framework to the commonly practiced methods that, if you've worked with statistics, that you are likely using or are familiar with. The reason that we might want to use these alternative methods is because they are far more flexible and therefore more powerful than these other methods: regression, generalized linear models, ANOVA, things like that, and many more. So in this first video, I just want to give the basic idea about MaxEnt and explain why it can be so useful and so powerful for statistical analysis. So to understand what maximum entropy is, we first have to say what entropy is. And before giving a very in-depth definition of entropy, I just want to start out by saying that it is proportional to the number of possible states a system can take on and the evenness of their distribution. Okay? So if a system has a lot of different possible states, and, well, that itself will tend to cause more entropy. And if the probability of any one of those states is roughly even, then there is still more entropy. Right? So if you look over to the image, you see a lower entropy in a higher entropy state. And you just notice that the higher entropy state, the more uncertain state, is like that. Although we may not rigorously understand why at this point, it is like that specifically because of how evenly spread out the probability of any particular state is. Now, the version of entropy that most people have learned about in, like junior high basic physics or whatever, is thermodynamic entropy. And kind of the obligatory example that gets used there is a box with particles in it, right? And so the entropy of this system, sometimes it gets called, disorder or something like that, the level of disorder. And I'm not a physicist, and I'm not gonna parse the specific definitions of what thermodynamic entropy is, but entropy in this setting increases with the number of possible states. So a larger box with more places for the particles to be. More particles will increase the entropy because more particles means more states of the whole system. More energy because that means they can take on a broader range of possible velocities, etc. So all of these things will increase entropy. And in this type of a setting, in this context, the word entropy has a physical interpretation. It is referring to something that is measurable about a physical system. Okay, but we in this whole series here are talking about informational entropy, and that is going to kind of rhyme with thermodynamic entropy, but it is in fact very, very different. The difference is that informational entropy, again the topic that we are concerned with, is not referring to the physical state of the system, but rather our uncertainty about the state of the system. So, of course, these two ideas are related. For instance, a physical system with more physical states will tend to cause more informational entropy because it increases our uncertainty about the state of that system, right? Because there's more possible ways it could be. But imagine the thermodynamic system, say that we cool the box, okay? Well, that will reduce the entropy, right? Because there's less energy, and so there's less possible velocities that the particles are moving at. But if we don't know that the box has been cooled, our informational entropy has not reduced. So, I mean, that's kind of a contrived example, but I hope that it draws the distinction between these two senses of the word entropy. So from here on out, if I say the word entropy, I am exclusively referring to informational entropy. So now when we come back to our first stab at trying to explain entropy, we can be a little bit more precise and no longer have to worry about saying that it's proportional to the number of possible states and the evenness of their distribution. Rather, we can say that it is the uncertainty over possible states, specifically our uncertainty over those possible states. Okay? So again, now if you look at the lower entropy and higher entropy images here, it becomes more clear why the blue left-hand figure there has lower entropy than the right figure. It's because in the left-hand figure, we can be more certain that the state of the system is that middle column there. Right? It's not always that middle column, but because some of the probability has concentrated there, there is less overall uncertainty in the system. But if we go to the right-hand side, we have higher entropy, and in fact, this is maximally uncertain because every possible state of the system is equally likely. So we are maximally uncertain. Okay? As we move forward, we'll kind of put some more rigorous teeth into this definition, but I hope that suffices for now. So now we can discuss what maximum entropy is. I'm going to say that maximum entropy is a philosophical stance and corresponding methods. Okay? And what is that philosophical stance? It is that we should claim maximal uncertainty unless we have information to the contrary. Okay? Now notice that if we're doing anything else other than this, we are essentially accepting as information bullshit. And I have this, I intentionally use this word as a technical term, which basically means, you know, kind of statements without regard for truth or falsehood. Okay, so that's what I mean here by bullshit. In other words, if we do anything other than assume our maximal uncertainty unless we have information to the contrary, then it is as though we are, knowingly or not, taking on board information that is not actually there. Okay? And that seems like a very, very bad idea when we're trying to learn about how a system works. And this kind of answers, you know, the next question, which is, why do we want to maximize entropy in the first place? Well, it's because we want our beliefs to correspond to reality. And because there are many more possible false beliefs than true beliefs, we want to be very discerning about the things that we admit as knowledge, say. And maximum entropy gives us a way of doing this in a very rigorous fashion. So that's why we want to maximize entropy, but why use MaxEnt methods? And this question may seem to answer itself given that last slide, but it's because you are missing a piece of the pie here, which is that most of the statistical methods that are commonly used, and maybe all of the methods that you use, are special cases of maximum entropy principles. Okay, so for instance, most of the probability distributions that you are familiar with, such as the normal or the binomial, etc., are distributions that are derived from MaxEnt principles, or derivable from MaxEnt principles. And so relatedly, a lot of the statistical procedures that are common, they're all based on, I shouldn't say all of them, but many of them are based on these probability distributions. And so they themselves are also related to maximum entropy. So knowing that, it emphasizes the question, why use MaxEnt methods? Why learn this alternative framework if probably most or all of our current methods are employing MaxEnt principles? And the answer is the following. The common probability distributions that we know and love, they are special cases of MaxEnt. They are the convenient cases. They are the cases that, when you solve a MaxEnt problem, have closed forms with analytical solutions that you could write down and calculate by hand, with pen and paper. Now, there's nothing wrong with these methods. They're incredibly useful and incredibly powerful, and they have carried statistics for, 100 or more years. But they were all developed before modern computing power. And so these special cases, again, special meaning that they have closed form expressions with analytical solutions, these do not represent all of MaxEnt probability distributions. Okay? There are infinite more that don't have closed form expressions, that you cannot solve analytically, that require numerical methods. And these numerical methods often require the use of computing power, which we now have readily available. And so by starting from a MaxEnt framework, we can, if we need to, use the tried and tested familiar methods and probability distributions that have always been used. But we're also able to generate custom-made probability distributions and methods specific to our data and the assumptions of our data and the information that we have about our data. And to do that requires numerical methods, and that requires computers. And that's really the focus of all of this, is using numerical methods to employ MaxEnt methods. So just to kind of be a little bit more explicit here about the difference between the standard approaches versus the MaxEnt framework. With the standard strategy, it basically comes down to trying to match the distributional assumptions of data and a model, right? You try to find a model that has assumptions that you're comfortable with your data. And if you can't find one, then maybe you try to transform your data to better conform to those assumptions. And a lot of times that is perfectly adequate and legitimate and okay. But sometimes it's not. Sometimes it's unsatisfactory, just on an intellectual level, and sometimes it produces, bad estimates. And this is where maximum entropy methods become very, very useful. So with MaxEnt methods, the emphasis is flipped. We declare our assumptions about the data, and then we generate the probability distribution that fits those assumptions or the information that we believe we have. So the goal here is not to abandon, long practiced and effective methods, the standard strategy, but to be able to have an alternative when those strategies are not as effective as we want them to be. And that's what MaxEnt, or at least the methods that we'll discuss here, thrive at. So, as we go forward in this series, the road ahead will look more or less like this. So we'll begin by learning how to find solutions to MaxEnt problems, and we'll start with some analytical problems, and what we will find on the other end are some of our closed form exponential family distributions like the binomial and normal distribution. Okay? But very quickly we will transition to numerical solutions. So numerical solutions will always work. We can find the same distributions that we did with the analytical approach, as well as distributions that don't have analytical solutions. Now, when we start using numerical methods, with our computer, we are essentially asking our computer to carry out many steps, sometimes tens or hundreds or maybe thousands, depending on the context of the problem, and the computer has to do this with bits. It's not your computer is digital, it's not analog, and this can create some numerical problems, some numerical instability. You get weird answers that can't possibly be right, and so we need to learn how to tell the computer how to do what we want it to do without the solutions blowing up. Once we kind of get our hands around that, we'll learn how to compare competing models, right? Often when we're creating a statistical model, we have several models that we're trying to compare. And so we'll learn how to measure the fit and compare the fits between different models. We will also learn how to prevent overfitting in our models. I guess I will leave discussion of that until later, but if you know about overfitting, the idea is to make sure that our model generalizes to data outside of our current sample. And then all of this in the last few chapters culminates in the MaxEnt analogs of things like regression, linear regression. Even nonlinear regression is just as easy as linear regression in MaxEnt. Generalized linear models, ANOVA, all of these things. That will be kind of the penultimate chapter. And then finally, we'll look at how to make inferences from our analysis, from our MaxEnt distribution, and analysis of that MaxEnt distribution. So how do we summarize the results? How do we test different hypotheses, I should say, and all the things that we are familiar with from our current and common statistical practices. We'll learn how to do those things with MaxEnt. So we begin with very, very basic principles, and then move forward until we are kind of neck deep in the methods that or MaxEnt analogous methods to what many of us are already using. Again, now with far more flexibility and hopefully power. If this goes well, there is much more to learn about this topic that goes into more advanced areas such as multivariate outcomes, missing data, hierarchical models, or what's sometimes called random effects or mixed effects models, etc. And so if this goes well, then I will invest the time to create that course and video series as well. So I hope that this is all going to be very helpful and useful for everybody. If you'd like to follow along in far more depth than what will be presented in these videos, then you can find a link to the full online course below.